In previous lecture, we have studied elastic deformation, which is a recoverable deformation, and it was time independent. Now we will study the anelastic deformation. Anelastic deformation is a recoverable deformation that occurs as a function of time. So what happens when you apply a load? Immediately the elastic strain occurs, but there are some elastic strains which occurs with time. So here time comes into the picture, and that is due to some relaxation process within the material. To understand this relaxation process within the material, probably you have seen some earthworm during rainy season. If you touch them, they will shrink. After some time, they will come back to its original position and start moving. So once it is shrinked and then it is come back to its original position, that it took some time within that, and we call it relaxation time. So that now earthworm is relaxed. So this relaxation time is different for different kind of material, different kind of relaxation phenomena. For atomic, it is 10 to the power minus 13, and for grain boundary relaxations, it goes up to 10 to the power 6 seconds. The fraction of relaxation process that is completed till time t can be defined by this equation. If t equal to tr, then value of x is only 0.63. It means that time given equal to its relaxation time is not sufficient to make him completely relax. Right? So to understand this time dependent recoverable deformation, let us consider an example of steel. Steel is basically an alloy of iron and carbon, and iron have BCC structure, right? This is the BCC, body centered cubic structure. Here the carbon remains at the edge centers here, and iron remains at the corner and one at the body. So it will, you know about the interstitial void. So this is the one kind of interstitial void where carbon is situated. Now the atomic radii of carbon is 0.71 angstrom, and the available space at this position is only 0.2 angstrom. So the carbon here is in the stressed state, very stressed state. Now let us suppose we are giving some kind of cyclic loading and unloading to this unit cell. So once you apply tensile load, this axis will stretch, right, and this axis will contract. So once this is contract, the iron will be here in very stressed state again, right? Now once the space become less here, so what this carbon will try to do, it will try to do from this position to this position where space is more. So jumping carbon from here to this position, this is a kind of a diffusion, solid state diffusion. It takes 100 seconds going over here, right? So this has been given in this picture. This carbon is going from his position to this position. Is it clear? Now consider three cases, because I said we are giving cyclic loading and unloading. Consider first case, I have elongated for 2 seconds and immediately released. So the cyclic loading and unloading time is 2 seconds. In another case, it is comparable to 100 seconds, say 120 seconds. And third is 10,000 seconds. Now, I'll make you understand the concept of time dependent. Why it is time dependent? Why this movement of carbon is time dependent? I give you an example. Let us suppose you have to drive from Patiala to Delhi. And I say, generally it takes 5 hours. And I say, I am giving you only 1 hour or 30 minutes or 1 hour 30 minutes to go Delhi. Will you able to reach? No. You will think, no, I am not able to reach because the distance is 250 kilometers and I have only 1 hour, so I will not able to make it out. So you will travel as per your ease. So time is not a parameter for you because this you can't do. Second case, if I say I give you 24 hours to reach Delhi, then again you will try as per your ease because time is too much and traveling time is only 5 hours. So your movement will again time independent. But if I say the traveling time is 5 hours and I am giving you 4 hours 45 minutes. So your movement from Patiala to, now you know you can make it. Your movement from Patiala to Delhi will be very, very time dependent. Probably you will not get down in between to have a cup of tea or have your meal. You will go through KFC, take some box and go ahead. So that is what does mean when the time is comparable to the given time, the process becomes time dependent. So this is the 3 example which has been given here. Now, first case, this one, the time is very, very, very less than the relaxation time. So there are 2 kinds of strain. I say one is the elastic strain and another I am saying it's a time dependent strain. These are my notations. So a material can show elastic strain and the strain due to relaxation process. So relaxation time is very, very less. So immediately when you stretch, the elastic strain comes, right? And there is no time to time dependent strains. So this will again go and come back. In this case, in the second case, when time is given very, very high, 10,000, there is some elastic strain plus time dependent strain, or you can say in this again I repeat here. So in terms of carbon movement, it is stretched, elastic strain, and then carbon is coming here, the strain due to carbon occupancy, that I am calling it the time dependent strain. So in the first case, you stretched, elastic strain occurs, but carbon was not having enough time to go from this position to this position. So the only strain remains elastic strains. Now the case 2, you stretched, elastic strain occurs, and carbon will also have a sufficient time to go over there, sit here and give some strain due to carbon occupancy. So net strain will be here. There are 2 kinds of strain. One will be the elastic strain and strain due to carbon. You can say carbon, due to carbon. I am saying this is due to carbon. Then again you release load, it will again follow the same path. Now in this case, so say here the strain is higher than the elastic strain. Now consider the third case where the given time or loading and unloading time is comparable to the relaxation time of carbon. So the U stressed, the elastic strain occurs here. You can say the elastic strain occurs. Now carbon, because time is comparable, now strain due to carbon occupancy. You release the load for 120 seconds again. First the elastic strain recovered, this portion, elastic strain recovered, and the recovery with time is the strain due to carbon occupancy. So in the first case, the path of elongation and release is same. The path is same, stretching, contraction. Here, initially the elastic strain, then strain due to carbon, release of elastic strain and release of carbon strain. So this becomes a loop like this, means the strains, the second in the reverse, it is lagging behind. So this shows as been as a loop, and the area under this loop is basically strain energy, elastic strain energy. So area under this loop is elastic strain energy, and this area under this curve is also equal to the heat generated within the material. So if the heat is generated, it should dissipate as fast as possible. That we call it as a damping capacity. We call it damping capacity. So material with good damping capacity are required to make base pads of machine to dump out the vibration. So lathe pads, where a lot of vibrations are there. In that vibration the heat is generated. That heat has to be dissipated fast. So we use those material which have good damping capacity, such as grey cast iron, polymers and rubbers. Material with low damping capacity are used in temple bells and piezoelectric device. So this energy loss during a cycle is frequency dependent. In common tires, the energy loss is high at a speed of 1000 kilometers per hour. We have discussed about elastic deformation. We also discussed anelastic deformation, which is time dependent recoverable deformation. Now today we will discuss plastic deformation, which is time independent non-recoverable deformation. To understand this plastic deformation, let's consider again the stress strain curve of a metallic specimen. This first curve, you are seeing that first again the linear portion, which was the elastic. When the yield point comes, the material transforms from elastic to plastic. Now this is a non-linear curve. Here, this part we call it, the material is plastically deformed and it will be non-recoverable now. This is a load elongation curve. If you divide this load by initial cross section area, it will become the engineering stress. If you divide by delta L over L, you make it, this is the engineering strain. This is the maximum load which a material can sustain. We also call it tensile strength. Above this, the necking starts here and finally it gets fracture. Now if you see in this region, you are increasing load, at the same time material is resisting. That's why this load is increasing. This portion we call it strain hardening of the material. The another way to understand this stress strain curve is by true stress and true strain curve. True stress means the applied load divided by instantaneous area, that P over AI, instantaneous area. And true strain can be expressed, say increase in the change in length is dl as a fraction of length L. At any instant we can calculate this true strain. This curve can be expressed in this power relationship. that is sigma equal to K into epsilon to the power n. N is the strain hardening exponent. Another way to define this stress in terms of strain rate, it is sigma equal to A into dE over dt m. Here n exponent tells you how the material will behave. So for example, for material like copper and some brass, this n value can be nearly 0.5. If the material is very hard, less ductile, then n value will be less. Any, say for example, heat treated steel, the n value is nearly 0.15, whereas for copper and brass the n value is 0.5. Now the point is that when you are applying a load, what actually is happening with the material? Say I am giving here, you all knows this is a say cylinder, copper cylinder. When you apply a load here, it will elongate, length will increase, diameter will decrease, but the volume will remain constant. Now I have a question. This much increase in length may be because of some reasons. Now what are those reasons? Is this the bond stretching? No, it is not bond stretching. So do you think that crystal structure of this copper will be changed after elongation? No, the crystal structure will remain same. So what actually is happening at microscopic level? There is no change in bond length, no change in crystal structure. Then what happened within that material that its length is increased? You will have to understand this first. So the two main mechanisms which causes the plastic deformation is slip and another is twinning. If you have a deck of cards, you apply shear force, what happens? The thickness will decrease and length will increase. The same way happening here, there is the slipping phenomena of atomic planes. Means atomic planes are sliding over each other in a step of one interatomic distance. Here the twinning, no complete step is created. Here just a distortion or a orientation change in this part. We will discuss later. But the main important mechanism by which plastic deformation takes place is this slip. Now to understand slip, what actually is happening in the slip, I am showing you one of the crystal. These are the different atomic planes. Now if I apply a tensile stress here, what will happen? These planes will slip on each other, right? This plane may slip. So you can say this becomes here slip, after slipping the length will increase. So this is a perfect crystal without slipping. Each material is having some kind of slip planes in it. Slip planes generally in material, those plane slips which is having highest planar density, they are more favorable to slip. And in which direction it slips? It slips in the dense pack direction. You have already done this calculation of planar density and linear density. So in the linear density, the number of atoms lying on that direction in the plane, the number of atoms lying on that plane. So those planes are prone to slip which are having highest planar density and highest linear density. Say for a FCC, this 111 plane is having highest planar density and it will slip in this direction or in this direction or in this direction. So the plane is 1, the direction is 3, so the slip system will be 1 plane, 3 direction, there will be 3 slip systems. So a slip plane and a slip direction, we call it slip system.